Welcome to Loops and Loops, your ultimate destination for all things deep learning. Whether you're a seasoned AI enthusiast or just dipping your toes into the world of neural networks, you're in for a treat. Join us as we unravel the mysteries of machine learning, dive into the latest research, and explore cutting-edge techniques in the realm of artificial intelligence. Get ready to expand your knowledge, sharpen your skills, and embark on a journey of endless possibilities with deep learning. So grab your headphones, settle in, and let's embark on this fascinating adventure together. Deep learning is a subset of machine learning that deals with algorithms inspired by the structure and function of the human brain, called artificial neural networks. Unlike traditional machine learning, which focuses on feature engineering and manual extraction of relevant information, deep learning aims to automatically learn hierarchical representations of data directly from raw input. Neural networks in deep learning are computational models inspired by the biological neural networks in the human brain. They consist of interconnected nodes or neurons organized in layers. Each neuron receives input signals, performs computations, and passes the output to the next layer of neurons, ultimately producing an output prediction. Deep learning models learn from data through a process called training. During training, the model is fed with input data along with corresponding labels or targets. The model adjusts its internal parameters iteratively through optimization algorithms such as gradient descent to minimize the difference between its predictions and the actual targets, thereby learning to make accurate predictions from new, unseen data. Common applications of deep learning include image and speech recognition, natural language processing, computer vision, autonomous driving, medical diagnosis, recommendation systems, and many others. Deep learning has demonstrated state-of-the-art performance in various domains, surpassing traditional machine learning techniques in tasks involving complex patterns and large-scale datasets. Advantages of deep learning include its ability to automatically learn hierarchical representations, handle large and unstructured datasets, and achieve superior performance in complex tasks. However, deep learning also has limitations such as the need for large amounts of labeled data, computational resources, and expertise in model design and optimization. A basic feed-forward neural network consists of an input layer, one or more hidden layers, and an output layer. Each layer is composed of interconnected neurons, and information flows forward from the input layer through the hidden layers to the output layer without feedback loops. Neural networks are trained using backpropagation, a technique that involves iteratively adjusting the model's internal parameters or weights based on the difference between predicted and actual outputs. Backpropagation computes the gradient of a loss function with respect to the model parameters and updates the weights to minimize the loss, thereby improving the model's predictive performance. Activation functions in neural networks introduce nonlinearity to the model, enabling it to learn complex patterns and relationships in the data. Common activation functions include sigmoid, tan rectified linear unit, and softmax, each serving different purposes such as introducing nonlinear transformations, handling vanishing gradients, or producing probability distributions. Different types of layers commonly used in neural networks include dense, fully connected layers, convolutional layers, pooling layers, recurrent layers, and normalization layers. Each layer type performs specific operations on the input data and contributes to the model's ability to extract features and make predictions. The number of layers and neurons in a neural network, known as its architecture, can significantly affect its performance. Increasing the number of layers and neurons can enhance the model's capacity to learn complex patterns, but may also lead to overfitting, where the model memorizes the training data and fails to generalize to new data. Finding the right balance in architecture design is crucial for achieving optimal performance. Convolutional layers in CNNs are designed to detect and extract spatial patterns and features from input images. Their purpose is to perform convolutions, which involve sliding small filter kernels across the input image, computing dot products at each position. This process enables the network to learn hierarchical representations of features, capturing local patterns such as edges, textures, and shapes. CNS handles spatial hierarchies of features by using multiple convolutional layers with increasing receptive fields. As the network progresses through layers, higher-level features are constructed by combining lower-level features, capturing more abstract and complex patterns at different spatial scales. This hierarchical approach allows CNNs to learn representations that are invariant to translation, rotation, and scaling. Pooling layers in CNNs are used to downsample the feature maps produced by convolutional layers, reducing their spatial dimensions while retaining important information. Pooling operations such as max pooling or average pooling aggregate information within local regions of the feature maps, helping to achieve spatial invariance, increase computational efficiency, and reduce overfitting by reducing the model's parameter space. Filter kernels in CNNs are small matrices of weights that are convolved with the input image. To produce feature maps, each filter kernel captures a specific pattern or feature, such as edges, corners, or textures, by learning the optimal combination of weights during training. By stacking multiple filter kernels in each convolutional layer, CNNs can learn to detect a diverse range of features across different channels. CNNs find applications in various computer vision tasks, including image classification, object detection, semantic segmentation, and image generation. They excel at recognizing patterns and structures in visual data, making them invaluable in areas such as autonomous driving, medical imaging, facial recognition, and surveillance systems. Recurrent neural networks are suitable for processing sequential data because of their ability to maintain temporal dependencies and capture long-range dependencies in sequences. Unlike feed-forward networks, which process input data independently, runners have recurrent connections that enable them to incorporate information from previous time steps, making them ideal for tasks involving sequences such as natural language processing, speech recognition, and time series analysis. Recurrent neural networks maintain memory of past inputs through hidden states, which are updated at each time step based on the current input and the previous hidden state. This recurrent nature allows RNs to capture temporal dynamics and dependencies in sequential data, enabling them to model sequences with variable lengths and learn patterns across multiple time steps. Training recurrent neural networks can be challenging due to issues such as the vanishing gradient problem, where gradients become extremely small as they propagate through many time steps, leading to slow convergence or unstable training. This problem arises because of the repeated application of the same weight matrix in recurrent connections, causing gradients to either vanish or explode during backpropagation. Long short-term memory networks are a type of recurrent neural network architecture designed to address the limitations of traditional recurrent neural networks, particularly the vanishing gradient problem and the difficulty of learning long-term dependencies. Long short-term memories introduce specialized memory cells with gating mechanisms that control the flow of information, allowing them to selectively remember or forget past inputs and gradients over multiple time steps, facilitating better gradient flow and more effective learning of long-range dependencies. Recurrent neural networks find applications in natural language processing tasks such as language modeling, machine translation, sentiment analysis, and text generation. They are also widely used in time series analysis for tasks such as forecasting, anomaly detection, and sequence prediction in domains such as finance, healthcare, and weather forecasting. Their ability to model sequential data makes them versatile and powerful tools for a wide range of applications requiring sequential processing. Optimization algorithms play a crucial role in training deep learning models by adjusting the model's parameters to minimize a predefined objective function, also known as the loss function. These algorithms iteratively update the model's parameters based on gradients computed from the loss function, aiming to find the optimal set of parameters that best fit the training data and generalize well to unseen data. Stochastic gradient descent is a widely used optimization algorithm in deep learning. It works by randomly selecting a subset of training samples called a mini-batch to compute the gradients of the loss function with respect to the model parameters. Stochastic gradient descent then updates the parameters in the direction that reduces the loss, typically multiplied by a learning rate. Variants of stochastic gradient descent, such as momentum, ATOGRAD, ERMS probe, and ATOM introduce modifications to improve convergence speed, stability, and performance in different scenarios. The loss function in deep learning quantifies how well the model's predictions match the true labels or targets in the training data. Its purpose is to measure the discrepancy between predicted and actual outputs, providing a feedback signal that guides the optimization process during training. Common loss functions include mean squared error for regression tasks, categorical cross-entropy for multi-class classification, and binary cross-entropy for binary classification. Gradients are calculated using backpropagation, a technique that computes the gradients of the loss function with respect to the model parameters by recursively applying the chain rule of calculus. During forward propagation, input data is passed through the network to compute predictions, and during backward propagation, gradients are computed layer by layer, starting from the output layer and moving backward through the network, allowing efficient computation of parameter updates. To prevent overfitting in deep learning models, several techniques can be employed, including regularization, dropout, early stopping, data augmentation, and model architecture design. These techniques aim to reduce the model's capacity to memorize noise and irrelevant details from the training data, promoting better generalization performance on unseen data. Activation functions introduce nonlinear transformations to the output of neurons in neural networks, enabling them to learn complex patterns and relationships in the data. Popular activation functions include a rectified linear unit, sigmoid, and tan, each serving different purposes such as introducing sparsity, handling vanishing gradients, or controlling the range of output values. Dropout regularization is a technique used to prevent overfitting by randomly deactivating a fraction of neurons during training. It works by probabilistically dropping out neurons along with their connections, forcing the network to learn redundant representations and increasing robustness to noise in the training data. L2 regularization penalizes large weights in neural networks by adding a regularization term to the loss function proportional to the square of the L2 norm of the model's parameters. This penalty encourages smaller weights, preventing the model from fitting the training data too closely and improving generalization performance on unseen data. Batch normalization is a technique used to improve training stability and accelerate convergence by normalizing the activations of neurons within each mini-batch during training. It works by computing the mean and standard deviation of activations across the mini-batch and then scaling and shifting the activations to have zero mean and unit variance. Batch normalization helps address issues such as internal covariate shift and vanishing gradients, leading to faster and more stable training of deep neural networks. Generative adversarial networks are a type of deep learning architecture consisting of two neural networks, the generator and the discriminator, which are trained simultaneously through adversarial learning. The generator generates synthetic data samples, such as images or text, while the discriminator tries to distinguish between real and fake samples through competition and cooperation. Generative adversarial networks learn to generate high-quality, realistic samples that are indistinguishable from real data. Transfer learning is a technique in deep learning where a pre-trained model, trained on a large dataset for a specific task, is fine-tuned or adapted to a different but related task with a smaller dataset. By leveraging knowledge learned from the source task, transfer learning enables faster and more efficient training on the target task, especially when labeled data is limited or expensive to acquire. Reinforcement learning is a branch of machine learning. concerned with training agents to make sequential decisions in an environment to maximize cumulative rewards. It is related to deep learning in that deep neural networks are often used to approximate value functions or policies in reinforcement learning algorithms, enabling agents to learn complex strategies and behaviors in domains such as gaming, robotics, and autonomous driving. Attention mechanisms in deep learning models like transformers enable the model to focus on relevant parts of the input data while performing tasks such as machine translation or text summarization. By assigning different weights to different parts of the input sequence, attention mechanisms allow the model to selectively attend to important information, improving performance on tasks involving long sequences or complex relationships. Challenges and limitations of current deep learning approaches include issues such as interpretability, robustness to adversarial attacks, data efficiency, and generalization to out-of-distribution data. Deep learning models may also suffer from overfitting, scalability issues, and lack of transparency in decision-making, posing challenges for deployment in real-world applications. In computer vision tasks like object detection and image classification, deep learning models analyze visual data to identify and classify objects in images or videos. They achieve state-of-the-art performance by learning hierarchical representations of features directly from raw pixel data, enabling tasks such as object localization, segmentation, and recognition in diverse and complex scenes. In natural language processing tasks like sentiment analysis and machine translation, deep learning algorithms process and understand human language to perform tasks such as analyzing sentiment in text, translating text between languages, and generating coherent text responses. Deep learning models such as recurrent neural networks, transformers, and attention-based models have revolutionized NLP by capturing semantic relationships and contextual information in text data. Deep learning in medical imaging and diagnosis involves using deep neural networks to analyze medical images such as X-rays, MRIs, and CT scans for tasks like disease detection, diagnosis, and prognosis. Deep learning models can achieve high accuracy and efficiency in medical imaging tasks, aiding clinicians in diagnosing diseases such as cancer, cardiovascular disorders, and neurological conditions. In autonomous vehicles, deep learning models are applied for tasks like object detection, classification, and tracking to enable safe and efficient navigation in complex environments. Deep neural networks process sensor data from cameras, LiDAR, and radar to detect and recognize objects such as vehicles, pedestrians, and traffic signs, facilitating decision-making and control in autonomous driving systems. In finance, deep learning models are used for tasks such as fraud detection, stock prediction, algorithmic trading, and risk management. Deep neural networks analyze large-scale financial data, including market prices, trading volumes, and transaction histories, to identify patterns, trends, and anomalies, enabling applications such as fraud detection, market forecasting, and portfolio optimization in financial markets. Ethical considerations surrounding the use of deep learning in sensitive areas like surveillance and healthcare include concerns about privacy, fairness, accountability, and potential misuse of technology. In surveillance, for example, there are worries about mass surveillance infringing on individuals' rights to privacy and freedom. In healthcare, issues such as data security, patient confidentiality, and biased algorithms can impact patient outcomes and trust in the healthcare system. Biases in training data can affect the performance and fairness of deep learning models by perpetuating and amplifying existing biases present in the data. For example, biased training data may lead to biased predictions or decisions resulting in unfair treatment or discrimination against certain groups. To mitigate biases, it's crucial to ensure diverse and representative training data, perform bias audits, and employ techniques such as data augmentation, fairness-aware training, and bias mitigation algorithms. To ensure transparency and accountability, In deep learning algorithms, measures such as model interpretability, documentation, and validation are essential. Techniques like model explainability, sensitivity analysis, and uncertainty estimation can provide insights into how models make predictions and help stakeholders understand their behaviour. Additionally, documentation of model development, training procedures, and data sources can promote transparency and reproducibility, while rigorous validation and testing ensure model performance and safety. The potential risks of deploying deep learning systems without proper validation and testing include inaccurate predictions, biased decisions, privacy violations, and unintended consequences. Without thorough testing and validation, models may make erroneous predictions or decisions, leading to harm or adverse outcomes for individuals or society. It's crucial to conduct rigorous validation, testing, and ethical assessments before deploying deep learning systems in real-world applications to mitigate risks and ensure safety and fairness. Deep learning can be used to address societal challenges, such as climate change and poverty, by analysing large-scale data, identifying patterns, and generating insights to inform decision-making and policy interventions. For example, deep learning models can analyse satellite imagery to monitor deforestation, predict climate patterns, and assess environmental impacts. In poverty alleviation, deep learning can help analyse socioeconomic data, identify vulnerable populations, and inform targeted interventions and resource allocation strategies. Popular deep learning frameworks include TensorFlow, PyTorch, Keras, and MXNet, each with its unique features and strengths. TensorFlow and PyTorch are widely used open source frameworks for deep learning development, offering extensive support for building, training, and deploying deep neural networks. TensorFlow provides a comprehensive ecosystem with high-level APIs, distributed training, and production deployment capabilities, while PyTorch offers dynamic computation graphs, intuitive APIs, and a flexible imperative programming style. TensorFlow and PyTorch differ in terms of usability and performance, with TensorFlow known for its scalability, deployment, and production readiness, while PyTorch is favoured for its flexibility, ease of use, and developer-friendly interface. TensorFlow's static computation graphs offer advantages in performance optimization and deployment, whereas PyTorch's dynamic computation graphs enable intuitive model development and experimentation. High-level APIs like Keras provide simplified interfaces and abstractions for building and training deep learning models, allowing developers to focus on model design and experimentation without worrying about low-level implementation details. Keras serves as a user-friendly interface to TensorFlow and other back-end frameworks, offering a simple yet powerful API for rapid prototyping, experimentation, and model deployment. Resources and tutorials available for learning deep learning with Python include online courses, books, tutorials, and documentation from platforms such as Coursera, Udacity, Fast.ai, and official documentation from TensorFlow and PyTorch. These resources cover topics ranging from deep learning fundamentals and neural network architectures to advanced techniques, applications, and best practices in deep learning development. Recent advancements in deep learning research include innovations such as self-supervised learning and few-shot learning. Self-supervised learning leverages unlabeled data to pre-train models on auxiliary tasks, enabling them to learn meaningful representations without requiring annotated labels. Few-shot learning focuses on training models to generalize from a small number of examples by learning to adapt quickly to new tasks or classes with limited data. Researchers are exploring the integration of neuroscience principles into deep learning models to better understand biological intelligence and improve the performance of artificial intelligence systems. By incorporating concepts such as synaptic plasticity, attention mechanisms, and hierarchical processing, researchers aim to develop more efficient, flexible, and adaptive neural network architectures inspired by the brain's structure and function. Explainability plays a crucial role in improving the interpretability of deep learning models by providing insights into how models make predictions or decisions. Explainable AI techniques such as feature attribution methods, model visualization, and saliency maps help users understand the factors influencing model outputs, increasing trust, transparency, and accountability in AI systems. Neural architecture search is a technique for automatically discovering optimal neural network architectures tailored to specific tasks or constraints. Neural architecture search algorithms explore a search space of candidate architectures using techniques like reinforcement learning, evolutionary algorithms, or gradient-based optimization, aiming to find architectures that maximize performance while minimizing computational costs. Neural architecture search has implications for model design by automating the process of architecture engineering, enabling the creation of custom design networks optimized for various applications. Deep learning techniques are being applied to address challenges in areas like climate science and drug discovery by analyzing large-scale data, modeling complex relationships, and generating insights to inform decision-making and research. In climate science, deep learning models analyze satellite imagery, climate simulations, and environmental data to predict weather patterns, monitor climate change impacts, and enhance understanding of Earth systems. In drug discovery, deep learning accelerates drug design, virtual screening, and drug repurposing by predicting molecular properties, identifying potential drug candidates, and optimizing drug development pipelines. Common metrics used to evaluate the performance of deep learning models include accuracy, precision, recall, F1 score, and area under the receiver operating characteristic curve. Accuracy measures the proportion of correctly classified instances, while precision measures the proportion of true positives among all predicted positives. Recall measures the proportion of true positives among all actual positives. And the F1 score combines precision and recall into a single metric. Receiver operating characteristic evaluates the trade-off between true positive rate and false positive rate across different classification thresholds, providing insights into the model's discriminative power and performance. Precision, recall, and F1 score differ in their emphasis on different aspects of classification performance. Precision focuses on minimizing false positives. Recall focuses on minimizing false negatives, and the F1 score balances precision and recall, making it suitable for imbalanced data sets, or when both false positives and false negatives are important. Cross-validation is a technique used to assess the performance of machine learning models. By splitting the data into multiple subsets, training the model on a subset of the data, and evaluating its performance on the remaining subset. Cross-validation helps estimate the model's generalization performance, detect overfitting, and optimize model hyperparameters by providing more reliable performance estimates than a single train test split. Confusion matrices are used to analyze the performance of classification models by summarizing the counts of true positive, true negative, false positive, and false negative predictions. Confusion matrices provide insights into the model's classification errors, such as misclassifications and confusion between different classes, helping diagnose model weaknesses and guide model improvement strategies. Considerations for deploying deep learning models in production environments include ensuring scalability, reliability, security, and efficiency. It's essential to optimize models for inference speed and memory footprint. Monitor model performance and drift over time, implement robust error handling and logging mechanisms, and adhere to privacy and regulatory requirements. Additionally, deploying models in production often involves integrating them with existing systems such as databases, APIs, or front-end applications, and establishing processes for model versioning, testing, and continuous integration and deployment. Model compression techniques like pruning and quantization improve the efficiency of deep learning models by reducing their size, computational complexity, and memory footprint. Pruning removes unimportant connections or neurons from the model, while quantization reduces the precision of model parameters, such as weights and activations, to lower bit width representations. These techniques enable faster inference, lower resource requirements, and deployment on resource-constrained devices like mobile phones or edge devices. Model serving is the process of deploying trained deep learning models to production environments and providing prediction or inference services to end users or applications. Model serving systems manage the deployment, scaling and monitoring of models, handle incoming requests, perform inference, and return predictions or responses to clients. Model serving plays a critical role in deploying deep learning systems by ensuring models are available, scalable, and performant in production environments. Challenges associated with scaling deep learning. Model to large datasets or distributed environments include data preprocessing, augmentation, model parallelism, communication overhead, synchronization, and fault tolerance. Scaling deep learning models requires efficient data pipelines, distributed training frameworks, synchronization strategies, and hardware accelerators to handle the computational and memory requirements of training on large datasets across multiple nodes or GPUs. Containerization orchestration tools like Docker and Kubernetes are used to deploy deep learning applications by encapsulating models, dependencies, and runtime environments into portable containers and managing their deployment, scaling, and lifecycle across distributed clusters. Containers provide isolation, reproducibility, and consistency in deploying models, while orchestration tools automate deployment tasks, ensure availability, and optimize resource utilization in dynamic cloud-native environments. Common debugging techniques used during the development of deep learning models include visualizing model architectures, inspecting intermediate activations, gradients, and weights, monitoring training metrics, and analyzing prediction errors. Debugging tools such as integrated development environments, debuggers, and visualization libraries help developers diagnose issues, identify bugs, and optimize model performance during training and inference. Visualization tools like TensorBoard help diagnose issues in neural network training by providing interactive visualizations of training metrics, model architectures, and computational graphs. TensorBoard enables developers to monitor training progress, analyze model behavior, identify performance bottlenecks, and debug issues such as vanishing or exploding gradients, overfitting or underfitting. Strategies for identifying and addressing overfitting in deep learning models include collecting more data, using data augmentation techniques, applying regularization methods such as L1, L2 regularization, dropout, or batch normalization, reducing model complexity, and early stopping. Overfitting occurs when models learn to memorize training data instead of generalizing to unseen data, leading to poor performance on test or validation datasets. Gradient checking is used to verify the correctness of backpropagation implementations by comparing analytical gradients computed using backpropagation with numerical gradients computed using finite differences. Gradient checking helps ensure the correctness of the gradient computation process and identifies implementation errors or numerical instabilities that may affect model training. Strategies for diagnosing and mitigating issues related to vanishing or exploding gradients include gradient clipping, batch normalization, using appropriate activation functions, initializing model parameters properly, and using gradient normalization techniques such as gradient scaling or layer normalization. Vanishing gradients occur when gradients become too small during backpropagation, while exploding gradients occur when gradients become too large, leading to slow or unstable training. These strategies help stabilize training, improve convergence, and prevent numerical instabilities in deep learning models. Transfer learning is a technique in machine learning where a model trained on one task is leveraged to solve a different but related task. It involves using knowledge gained from solving one problem to help solve a different problem, typically by transferring learned features or representations from a pre-trained model to a new model. pre-trained language models like bidirectional encoder representations from Transformers and GP3, which is Generative Pre-trained Transformer 3, are large-scale neural network architectures trained on massive text corpora. They learn to understand and generate natural language by capturing semantic and syntactic patterns from the text data. Fine-tuning involves taking a pre-trained language model and adapting it to a specific natural language processing task, such as text classification or language generation, by updating the model parameters on a smaller task-specific dataset. Feature extraction in transfer learning refers to the process of extracting relevant features or representations from a pre-trained model for a new task. Fine-tuning, on the other hand, involves updating the parameters of the pre-trained model along with additional task-specific layers to adapt it to the new task. Feature extraction is commonly used when the new task is similar to the original task, while fine-tuning is preferred when the new task is sufficiently different or requires more adaptation. Common architectures used for transfer learning in computer vision tasks include convolutional neural networks such as very deep convolutional networks, ResNet and MobileNet. These architectures are pre-trained on large image datasets, like ImageNet, and learn to extract hierarchical features from images, which can be transferred and fine-tuned for various downstream tasks such as object detection and image classification. The choice of pre-trained model architecture can significantly affect the performance of fine-tuning. Different architectures may capture different levels of abstraction and semantic information from the data, leading to variations in performance depending on the specific characteristics of the task and dataset. Automated machine learning is a set of techniques and tools that automate various aspects of the machine learning pipeline, including data pre-processing, feature engineering, model selection, hyperparameter tuning, and model evaluation. AutoML streamlines the process of model development, reduces the need for manual intervention, and democratizes machine learning by making it accessible to users with varying levels of expertise. Automated machine learning techniques can be used to automate tasks such as feature engineering and model selection by automatically generating and evaluating a wide range of features and model architectures. This helps identify the most effective features and models for the given dataset and task, saving time and effort compared to manual experimentation. Hyperparameter optimization is the process of searching for the best set of hyperparameters for a machine learning algorithm to optimize its performance on a given dataset. Hyperparameters are parameters that are set before the learning process begins, such as learning rate, batch size, and network architecture. Hyperparameter optimization is important in deep learning because the choice of hyperparameters can significantly impact the performance and convergence of the model. Algorithms and approaches used for hyperparameter tuning include grid search, random search, Bayesian optimization, and evolutionary algorithms. These techniques systematically explore the hyperparameter space, evaluate the performance of different configurations, and iteratively refine the search to find the optimal set of hyperparameters. Interpretability is important in the context of deep learning models because it helps users understand how and why a model makes certain predictions or decisions. This is crucial for building trust, verifying model behavior, debugging errors, and identifying biases or unintended consequences in the model's outputs. Techniques for interpreting the predictions of black box models. Like deep neural networks include model-specific methods such as activation maximization, feature visualization, and layer-wise relevance propagation, as well as model-agnostic approaches like shapely additive explanations values. Local interpretable model-agnostic explanations and permutation feature importance. Feature importance quantifies the contribution of each input feature to the model's predictions. For deep learning models, feature importance can be calculated using techniques such as gradient-based attribution methods, which measure how changes in input features affect model predictions by computing gradients with respect to the inputs. Techniques like saliency maps and gradient-based attribution visualize the sensitivity of model predictions to changes in input features by highlighting regions of the input space that have the greatest impact on the model's output. Saliency maps show the gradient of the model's output with respect to the input features, indicating which features are most influential for a given prediction. Challenges associated with achieving both high performance and interpretability in deep learning models include the complexity and nonlinearity of model architectures, the trade-off between model complexity and interpretability, and the potential for overfitting interpretability methods to specific datasets. Federated learning is a decentralized machine learning approach where model training is performed on distributed devices such as smartphones or IoT devices instead of a centralized server. Federated learning enables collaborative model training while keeping data localized on the devices, thereby addressing privacy concerns associated with centralized model training. Federated learning helps address privacy concerns by ensuring that sensitive data remains on users' devices and is not directly accessible by the central server. Only model updates, example gradients, are shared between the devices and the server, preserving the privacy of individual user data. Differential privacy is a framework for quantifying the privacy guarantees of data analysis algorithms. It ensures that the presence or absence of a single individual's data does not significantly affect the outcome of the analysis, thereby protecting individuals' privacy. In deep learning, differential privacy can be achieved through techniques such as adding noise to the training data or gradients during model training. Techniques for ensuring data privacy and confidentiality in federated learning settings include secure aggregation protocols, encryption techniques such as homomorphic encryption, and decentralized identity management systems. These techniques help protect the privacy of users' data and prevent unauthorized access to sensitive information during federated model training. Federated learning frameworks like TensorFlow Federated provide tools and libraries for implementing privacy-preserving machine learning models in federated settings. TensorFlow Federated abstracts away the complexities of federated learning, allowing developers to focus on building privacy-preserving models and deploying them in distributed environments. Model compression refers to techniques used to reduce the size and computational complexity of deep learning models, making them more efficient for deployment on resource-constrained devices such as smartphones, IoT devices, and embedded systems. It is important for deploying deep learning models in real-world applications, where memory processing power and energy consumption are limited. Techniques like pruning and quantization reduce the computational and memory requirements of deep learning models by removing redundant parameters and reducing the precision of model parameters, respectively. Pruning removes unimportant connections or neurons from the model, while quantization reduces the number of bits used to represent model parameters, leading to smaller memory footprints and faster inference speeds. Knowledge distillation is a process where a large, complex model, which is teacher model, transfers its knowledge to a smaller, simpler model, which is student model, by distilling the teacher model's predictions into a more compact representation. This helps compress the knowledge contained in the teacher model into a smaller model, reducing memory and computational requirements while maintaining performance. Challenges associated with compressing deep learning models while preserving their performance include balancing compression with performance trade-offs, avoiding significant drops in accuracy or generalization ability, ensuring compatibility with target deployment platforms, and managing the complexity of compression techniques and workflows. Frameworks like TensorFlow Lite and ONNX runtime support the deployment of compressed models on edge devices by providing optimized runtime environments and libraries for executing compressed models efficiently on various hardware platforms. They enable developers to deploy compressed models seamlessly on resource-constrained devices without sacrificing performance. Ethical considerations associated with the development and deployment of deep learning models include concerns about fairness, accountability, transparency, privacy, security, and bias. These considerations are important for ensuring that deep learning systems are developed and deployed responsibly and ethically, with consideration for their potential societal impacts and consequences. Biases in training data can lead to unfair or discriminatory outcomes in deep learning applications by perpetuating and amplifying biases present in the data. Biased training data can result in models that exhibit unfair or discriminatory behaviour, such as favouring certain demographic groups or perpetuating stereotypes. Algorithmic fairness is the principle of ensuring that machine learning models make decisions that are fair and unbiased across different demographic groups. It involves identifying and mitigating biases in training data, model design, and decision-making processes to ensure equitable outcomes for all individuals. Measures that can be taken to promote transparency. Accountability and fairness in deep learning systems include documenting data sources and pre-processing steps, evaluating models for bias and fairness, providing explanations for model predictions, and soliciting feedback from diverse stakeholders. Additionally, adopting transparent and ethical development practices, adhering to regulatory guidelines and standards, and fostering interdisciplinary collaboration can help promote responsible and ethical AI development. Frameworks like the Ethical AI Toolkit and Fairness indicators support the ethical development and evaluation of deep learning models by providing tools, guidelines, and resources for assessing and mitigating ethical risks and biases in AI systems. These frameworks help developers integrate ethical considerations into the AI development lifecycle and evaluate the fairness and transparency of AI models in real-world applications. Common challenges during training of deep learning models include overfitting, vanishing or exploding gradients, lack of labeled data, and computational resources. Techniques like regularization, dropout, batch normalization, and early stopping can help address overfitting. Gradient clipping, weight initialization strategies, and using different optimization algorithms can mitigate vanishing or exploding gradients. Data augmentation, transfer learning, and semi-supervised learning can alleviate the need for large labeled datasets. Utilizing cloud computing resources or distributed training frameworks can address computational limitation. Ensemble learning combines predictions from multiple individual models to improve overall performance. In deep learning, ensembles can be created by training multiple neural networks with different architectures, initializations, or training data. Combining diverse models helps capture complementary patterns in the data, reducing variance and improving generalization. Hyperparameters control the behavior and performance of the model during training. Unlike model parameters, which are learned from data example weights and biases, hyperparameters are set manually before training and include parameters like learning rate, batch size, and network architecture. Optimizing hyperparameters is crucial for achieving optimal model performance. Learning rate schedules adjust the learning rate during training to improve convergence and stability. Common schedules include step decay, exponential decay, and cyclic learning rates. Learning rate schedules help prevent the model from overshooting or getting stuck in local minima by adjusting the learning rate based on the training progress. Data augmentation involves applying transformations to the training data to increase its diversity and size, improving the model's ability to generalize to unseen examples. Common augmentations include rotation, translation, scaling, flipping, and adding noise. Data augmentation helps expose the model to different variations of the training data, making it more robust to variations in the test data. Transfer learning leverages knowledge from pre-trained models on large datasets to bootstrap the training of new models on smaller datasets or different tasks. By transferring learned features or representations, transfer learning accelerates training, reduces the need for large amounts of labeled data, and improves generalization. Imbalanced data sets pose challenges as models may become biased towards the majority class, leading to poor performance on minority classes. Techniques like class reweighting, data resampling example oversampling, undersampling, and generating synthetic samples can help address class imbalance, ensuring balanced representation during training. Multimodal deep learning models integrate information from different modalities, example, text, images, audio, to improve performance. Techniques like fusion layers, multitask learning, and attention mechanisms enable models to effectively process and combine information from diverse inputs, enhancing their understanding and performance across tasks. Adversarial examples are inputs deliberately crafted to cause misclassification or errors in deep learning models. They pose a challenge to model robustness and security. Defenses against adversarial attacks include adversarial training, robust optimization, and adversarial detection methods, which aim to make models more resilient to adversarial perturbations. Domain adaptation addresses the problem of domain shift, where the distribution of data in the training and test domains differs. By learning domain invariant features, domain adaptation enables models to generalize across domains, improving performance on unseen data. Techniques include adversarial domain adaptation, domain adversarial neural networks, and instance weighting methods. Autoencoders are unsupervised learning models that aim to learn efficient representations of input data by encoding it into a lower dimensional space and then reconstructing it from the encoded representation. They consist of an encoder network that compresses the input data into a latent space representation and a decoder network that reconstructs the input from this representation. Applications of autoencoders include data denoising, dimensionality reduction, anomaly detection, and generating new data samples. Attention mechanisms enable deep learning models to focus on relevant parts of the input data while performing tasks like machine translation, natural language processing, and image captioning. By dynamically weighting different parts of the input sequence, attention mechanisms improve the model's ability to capture long-range dependencies and context, leading to better performance in tasks requiring sequential or hierarchical processing. Graph neural networks extend traditional neural network architectures to handle graph-structured data, where nodes represent entities and edges represent relationships between them. Graph neural networks aggregate information from neighboring nodes and edges to generate node embeddings, capturing both local and global graph structure. They are used in tasks like social network analysis, recommendation systems, and molecular modeling. Self-supervised learning is a form of unsupervised learning where models learn to predict certain parts of the input data based on other parts of the same data. It leverages the inherent structure or redundancy in the data to create supervised learning signals without explicit labels. Self-supervised learning has advantages in training deep learning models with unlabeled data, as it enables models to learn useful representations without requiring manual annotation. Reinforcement learning is a type of machine learning where agents learn to make sequential decisions by interacting with an environment to maximize cumulative rewards. Unlike supervised learning, where models are trained on labeled data, and unsupervised learning where models learn patterns in unlabeled data, reinforcement learning learns from feedback received as a result of actions taken in the environment. Deep Q-learning is a popular reinforcement learning algorithm that uses deep neural networks to approximate the action value function, enabling agents to learn complex decision-making policies. Ethical considerations surrounding the use of deep learning models for predictive policing and criminal justice systems include concerns about bias, fairness, accountability, transparency, and privacy. Deploying AI systems in law enforcement raises questions about the potential amplification of existing biases in the data, the fairness of algorithmic decisions, and the impact on individuals' rights and liberties. Deep learning techniques can be applied to address challenges in environmental monitoring And sustainability by analysing large-scale environmental data, modelling complex systems, optimising resource utilisation, and predicting environmental outcomes. Applications include climate modelling, natural disaster prediction, pollution monitoring, wildlife conservation, and sustainable agriculture. Interpretability in deep learning refers to the ability to understand and explain the decisions made by AI systems. It is important for building trust, transparency, and accountability in AI systems, especially in critical domains like healthcare, finance, and criminal justice. Interpretability techniques enable users to understand how models arrive at their predictions, diagnose model failures, detect biases, and ensure ethical and fair decision-making. Emerging trends in deep learning research include neurosymbolic AI, which integrates symbolic reasoning with neural network-based learning to enable more human-like reasoning and understanding, and meta-learning, which focuses on algorithms that can learn to learn by acquiring knowledge from previous tasks and experiences to adapt to new tasks more efficiently. These trends hold promise for advancing the capabilities and applications of deep learning in various domains. And that's a wrap for today's episode of Loops and Loops. We hope you enjoyed delving into the depths of deep learning with us. Remember to hit that like button, share with your fellow enthusiasts, and subscribe to our channel for more captivating content. Keep exploring, keep learning, and keep pushing the boundaries of what's possible with deep learning. And until next time, stay curious, stay inspired, and keep those neural networks looping. Thanks for tuning in.